Hey everybody, this is another example solving a trig equation. This one is sort of level 2. If the example 2 sine squared theta minus 3 sine theta plus 1 equals 0, which hopefully you were just watching that video, if that were to be considered like level 1. Really a level 1 equation wouldn't have second power, so we'll say, these are levels are corresponding to equations that have quadratic trig expressions in them. So something to the second power. This will be a little bit more challenging than the previous example. All right, solve the following trigonometric equation in the interval. And now my interval this time is written using interval notation. The square bracket means that 0 is included, and that's where we begin, comma, sorry, my dog. Shh. From 0 to 2 pi, and the parenthesis means that value is not included. So it's sort of like a less than or greater than symbol would be associated with 2 pi, and then the less than or equal to, greater than or equal to symbol would be associated with 0. This also tells us our answer should be written in radians, not degrees. If it were degrees, this would say 0 degrees, and this would say 360 degrees. I gave you a hint. You won't always get a hint. The hint is to rewrite as a single trig function. So I don't want to have secant and tangent in the same equation. So you want to think back to the fundamental trig identities and think if there's something there that you can use, and you want to be efficient. There is more than one way to do this. However, we want to be efficient and get this done clean, neat, and in as few steps as possible. So what would be the best option here? Well, hopefully when you see secant squared and tangent squared, even if only one of them were squared in this equation, so keep that in mind, and I'll try to talk about it in this video. If not, I'll just save it for another one. You should still see that when the two of those are together, secant and tangent, and one of them at least is squared, that you can sort of start to see that Pythagorean identity that includes the two of them in your head. Now, the original numero uno Pythagorean identity that everybody learns is sine squared theta plus cosine squared theta equals 1. If that's the only one you truly have memorized, that's fine. You use that to figure out the other two. If I want tangent in my new identity, and I know from the quotient identity that tangent is sine over cosine, I'm going to divide everything in the original identity by cosine squared theta. From there, I will get sine squared theta over cosine squared theta, tangent squared theta. Next, cosine squared theta over cosine squared theta is 1. And next, 1 over cosine squared theta, since 1 over cosine is secant by the reciprocal identity, then if I square the top and bottom, 1 squared is still 1, cosine squared is cosine squared. This side will equal secant squared theta. Now, it's really up to you which one you're more comfortable with. If you have a hard time with tangent and remembering, which ratios go with which angles, yada, yada, then change everything into secant. Because secant is just the reciprocal of cosine. So if you know sine and cosine really well, maybe this is actually easier, even though you might think like tangent's one of the 3 originals, so cot𝜃, sine, cosine, tangent. Well, maybe this is actually easier. So by taking one extra step, I'm going to subtract 1 from both sides and rearrange this identity so that tan squared theta is isolated. And I see here that it's equal to secant squared theta minus 1. Then I'm going to take this difference over here, this little subtraction piece, and I'm going to fill that in everywhere I have a tangent squared, which is really only in one place right there. So let's go to the next step. Make sure we use parentheses. We will have 3 secant² minus 2 times the quantity of, fill that in, secant² minus 1 minus 4 is 0. Now I'm going to distribute. The reason I didn't model it with distributing in one step is a lot of people mess up. Okay, so minus, negative, or negative minus, minus minus, whatever. Two negatives make a positive. 3. Secant², this is minus 2 secant² plus 2 minus 4 is 0. 3 secant² minus 1 secant². 3 apples minus 2 apples is 1 apple. Okay, so this is 1. We don't need to write the 1. I'm being a little extra. Secant² right there. Now a positive 2 minus 4 is minus 2 is 0. Add 2 to both sides. Secant² equals 2. Maybe you're pretty good at knowing that that means cosine² equals 1/2. Maybe you're not. We'll go both routes. Take the square root of both sides. We've discussed many times since Algebra 2 that when you are the person responsible for taking the square root in a problem, it is important that you include both the positive and negative answers. Hope you remembered that by yourself. Same concept here if you chose to go this route. Cosine theta, because that's the square root of cosine², is positive and negative. Now be careful here. I feel like when people see 2s and 1/2 and they think taking a square root, they either by accident leave the 1/2 the same because you're like, oh, it's already on the unit circle and it's so convenient, and you just go with the 1/2, or you kind of take a roundabout way to do it. The square root of 1 is 1. The square root of 2 is √2, right? It's irrational. You can't get a nice whole number. 1 over √2, well, that's the reciprocal of √2. And we also, in an earlier unit, in fact, the first unit in this class where we did simplifying radicals, we worked on memorizing that the reciprocal of √2 is √2 over 2, and so on and so forth, okay? So after all is said and done, the square root of 1/2 is is √2 over 2. You might want to make a note of that. The square root of 1/2 equals √2 over 2. We don't want to take 10 hours for you to do square root of 1, square root of 2, 1 over square root of 2. Multiply on top and bottom by square root of 2. You got √2 over 2. Like, we're getting old waiting for you to finish, okay? So know it, okay? Don't accidentally square it and make it a 4th. If you start seeing numbers that aren't on the unit circle in your work, and the question never mentions finding an approximate answer, which is what it will say when you need a calculator, that means you don't need a calculator. That means it's on the unit circle, and that means 1/4 is weird, all right? Because that's not on the unit circle. Anyhow, in either case, the way we read these questions is we say the secant of what angles or angle equals positive and or negative √2. The cosine of what angle or angles equals positive and negative √2 over 2. I'm looking for both answers. There are 2 places where these equal the positive form of it, and there are 2 places between 0 and 2 pi on the unit circle where it equals the negative. We should get 4 answers altogether. Secant theta equals positive √2 when theta equals, am I covered up a little? Yeah, there we go. Something over there. And secant theta equals negative √2. Always really make sure that's not my best writing. I try not to let it touch the root. Sorry, I'm using a pen because it looks like that square root where people, put the little tail on the radical. So just be careful that you don't confuse yourself. Theta equals And then this is really the same concept. So cosine theta equals positive root 2 over 2, and cosine theta equals, see, I'm going to try to do it better here, negative root 2 over 2. Okay? Theta equals and theta equals. Root 2 over 2 is approximately 0.7. The other unit circle numbers other than 0 and 1 are a half, which is 0.5, and root 3 over 2, which is about 0.87. That makes root 2 over 2 the one in the middle, the more medium-sized amount. So cosine is the x. So for which angles do you move to the right, positive? Do you move to the right, that medium amount, for which tick marks on that unit circle? And then to the left, that medium amount. In either case, that's what we're looking at. So we move to the right, that medium amount for the angles, right in the middle there, right in the middle there. What are they? Quadrant 1, we have pi over 4. And then here in quadrant 4, we have 1 pi over 4, ready? 2, 3, 4, 5, 6, 7 pi over 4. Okay? And then, sorry about the ringing, it's my buzzer. Can I pause this? Yes. Give me 1 minute. Okay. I think I'm recording again. Yeah, sorry. Again, if I were counting, so if this is 1 pi over 4, and I counted up from there, 2, 3, 4 pi over 4, which is pi, 5 pi over 4, 6 pi over 4, 7 pi over 4. That is where cosine is positive, then negative would be that same spot on the left. We just counted those out, so we have 3 pi over 4 and 5 pi over 4, and these two here are the same question, same answer. There you go. Hopefully we can see that. And like the other examples, I'm just going to try to go in over here and highlight a little bit so that we can see where everything came from. I'll even indicate it a little bit on the unit circle. So this goes with those two answers, and it's actually compatible with this. Again, you don't need to change it to cosine. Maybe, there you go. You don't need to change it to cosine. It is actually fine the way it's written right there. And then those two answers go with that right there. There we go. So we have 4 answers total. Basically all of the angles that have a reference angle of pi over 4, which are pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. If I had opted to solve using the fact that secant squared theta is equal to tangent squared theta plus 1, instead of the fact that tangent squared equals secant squared minus 1, then my entire equation would have tangent in it instead. And seeing now that the answers are pi over 4, 7 pi over 4, 3 pi over 4, and 5 pi over 4, that means that as I solved, I should have ended up with tan squared theta equals 1, which maybe would have been easier for you. Maybe you're good at knowing, oh, I know, tan equals 1 and negative 1 at the pi over 4s, 1, 3, 5, and 7 pi over 4. But maybe you mix up the ones where it's root 3 over 3 and root 3. Maybe you can't keep it straight. So it's up to you, okay? I know this was a little bit extra, but one thing that did make it easier is you didn't need to factor this example with AC method, because when we worked it out, we ended up being able to solve by taking square roots, since we didn't have that linear term, that term to the first power. And like I mentioned at the very beginning of the video, if the original problem only had one of those trig functions squared, then that would be the one. So for instance, pretend that it only had tangent squared, and this was secant theta to the first, like no exponent or no visible exponent. Then I would definitely change tangent to secant, because you can't change the non-squared one using Pythagorean identity. You have to change out the one that's squared using the Pythagorean identity. And like I said, we'll see examples like that when we move along. And actually, I think in the next one, it's sort of got that layer of that built in. So I hope this helped. I hope you kind of understand. Maybe you can try it using tangent the way I just described and see that you get the same answer. But if you understand, give the video a thumbs up. If you don't understand any more examples like this one, give the video a thumbs down. No shame in that. I don't know who does what. I'm just using that for inventory. Okay? Have a good day.